Okay, welcome back. This is the last lecture of this summer semester series, and I would like to sort of summarize where we are, in particular say what are the consequences that we can immediately draw from non-collapsing, and then also say a few words about what else can be done then in the future. Okay, so let's start. Consequences of non-collapsing. And quickly recall what we had shown. We had shown that if Mn g of t is a solution of Ricci flow on a closed manifold, and say on some finite time interval, and then if R0 is such that the scalar curvature at the final time this time interval is less than R0 to the minus 2, which is of course less than R to the minus 2 for R less than R0 on a ball of radius R around any P in the manifold. So if we have curvature control, scalar curvature control on the final time, then there exists some xc greater than 0 depending on the initial metric, the length of the time interval, and R0 such that the volume ratio, which is the volume of the ball around P at radius R divided by R to the n, is bigger than xc. So we have a lower bound in the volume rate. Now, the first consequence is, if you remember that when we proved the pinching theorem in the positive curvature case, at some stage we invoked Klingenberg's lemma in order to be able to compare the volume in a small ball to the curvature if the curvature is between 1 and 1/4. But what we really needed is at that point the injectivity radius. Here, with this proof, we would immediately get the relation between volume in a small ball and the curvature. So we wouldn't need Klingenberg's lemma in that positively curvature case. But on the other hand, in the general case, we want to turn this around, and it's a well-known fact that once you have this non-collapsing in the volume, that then, using Klingenberg's lemma, you can get a proof of the lower bound on the injectivity radius. This is a statement that is completely independent of any flow, so I just state this statement from geometry, a proof you can find in the lecture notes of Peter Topping. Let's just collect this result on the injectivity radius. So there exists a universal number r independent of anything, and there exists an eta which just depends on the dimension, such that on any manifold, on any closed Riemannian manifold, Mn, dimension n, metric G, with curvature with respect to G bounded by 1, so we fix the scale, which of course has to do with this radius. If you have a different bound here, you have to scale this r bar. Then there exists a point in the manifold such that the volume ratio at this point is a lower bound for the injectivity radius of the manifold, and of course the injectivity radius of the manifold is the infimum over all points in the manifold of the injectivity radius of the manifold at that point. And you want this inequality here for all r. Up to r bar. Okay. So you can bound the injectivity radius from below in terms of the volume ratio. And this means, of course, now if we combine this with our non-collapsing result, it means that if we have a solution of Ricci flow which has a certain curvature bound, then we get a lower bound on the injectivity radius depending on that curvature bound. So as a corollary, we get that suppose Mn G of t is the solution of Ricci flow on some interval finite on a closed manifold. And suppose that you have a bound, a uniform bound on the whole Riemann tensor by, say, a constant k squared on the whole time interval. So typically this would be applied with a time just before the maximal time, so that you still have such a curvature bound, k. Then there exists a number xc, just depending on the initial metric and the length of the time interval, such that the injectivity radius of the metric at time t is bigger than xc times k to the minus 1 for all t in the time interval. And the proof is clear. We have, you just choose, in order to apply the proposition, you have to rescale the number R bar in that opposition by K and choose R0 to be K to the minus 1 times, actually 1 over n times n minus 1, because then you get the scalar curvature bounded by R0 to the minus 2. The scalar curvature consists of n times n minus 1 sectional curvatures, so the bound on the sectional curvature translates into a bound on the scalar curvature, where you have to take a constant depending on n, and then you get this condition for all r between 0 and R0, and you get this out of this assumption here on the curvature, and then you get that also from here you get that the volume ratio is less than eta on R times the injectivity radius of m and g of t for all r up to R1, and for R1 you take the the minimum of this R0 and the R bar that appears in the here's the R bar, and then there's the R0. And the R bar, okay, the R bar has to be rescaled times k to the minus 1, and then you get that the injectivity radius of mn at g of t is bigger than some number depending on n times k to the minus 1 times the xi. Well, that's so. Okay. Right. So the upshot is, if we have a solution of Ricci flow, because it is non-collapsed with some number initially, then Perelman's monotonicity, like in last lectures, gives us that we have non-collapsing at the later time because of the monotonicity of the W functional, and this later time, of course, could be any time in this time interval between 0 and t. Therefore, we get the non-collapsing on the whole time interval. Therefore, on the whole time interval, we have this lower bound on the injectivity radius. Now, the lower bound on the injectivity radius now is the key thing that allows one to prove a compactness theorem for sequences of Riemannian manifolds, and as a consequence also a compactness theorem of sequences of solutions of Ricci flow. And this is exactly what occurs when you try to rescale a singularity. So I think I can briefly explain without proof what is the concept of convergence that you need for Riemannian manifolds. In the proof of the first major theorem, the pinching theorem in the positive case, we got away with proving convergence in a very strong sense, namely we could always choose the same coordinate system and get the convergence of the metric in a fixed coordinate system. And that was the case because in this pinching theorem, in the positive case, the convergence to the round metric is so incredibly fast. So we got away with just fixing the coordinate system and the metric would converge. Now, in the general setting, that is not good enough. And you can imagine why. We've already seen that a key thing that comes up in the monotonicity formula of Perelman is the role of this function f and the diffeomorphism induced by the gradient of f, which is a tangential diffeomorphism, and we expect some of the solutions that become out of these rescaling procedures to be solutions that are solitons, in other words, move along the gradient of a function on the manifold by diffeomorphism. So the concept of convergence has to allow the need to change the coordinate system as we go along the sequence of manifolds and solutions of Ricci flow. So the concept has to somehow be adapted to the possibility of changing the coordinate system, the possibility to have diffeomorphisms in tangential direction, and which also means that we have to somehow make sure at what point, at what region of the manifold we look. And this leads to a concept of pointed convergence developed by Giga and Gromov. Compactness for sequences of Riemannian manifolds or families of it, because we want to take sequences of flows, sequences of Riemannian manifolds in the sense of Giga and Gromov, in the sense of pointed convergence of Giga and Gromov. Right, so let me do it right away for families of manifolds of Riemannian matrix. So definition. If you like, you can first forget the t variable, just think of Riemannian manifolds, it's already interesting in that case. So suppose Mi with matrix Gi, which I want to allow to depend on time, is a sequence of smooth families of Riemannian manifolds and if there's a time interval, we assume first of all the manifolds are complete. And if there's time intervals, we assume that t is in some interval which may be infinite or finite. We have this family, and then we assume that there's points in these manifolds. This is fixing the region where we want to take limits. And now suppose there is another Riemannian manifold, possibly family of matrix. This is going to be the limit. Is a smooth family of Riemannian manifolds. With again, time interval in AB, and suppose there is a point P in the manifold, in this limiting manifold. So now we say that the triple mi gi of t with points pi converges in the sense of Cheever-Gromov to the manifold g of t at the point P if the following is true. So we have to first say, because the limit in the end may be a non-compact manifold. Think of rescaling some neck. Then we start with something compact, we rescale the neck, and then in the end we expect to get a cylinder. So although these guys here may all be compact, we have to allow for the fact that this guy is non-compact. So we first need a compact exhaustion of this manifold. So if there exists a sequence of compact I should say relatively compact omega I inside mi such that the omega I exhausts all of Mn as I tends to infinity. And also I need this point P to lie in all these domains. And if secondly there exists now a sequence of diffeomorphisms relating the mi's and the m, the clever way is to make the map go from m, from the limit, back to the mi's. So if there exists smooth phi mapping from the target, this is the limit, the set in the limiting manifold, back to the mi, which are diffeomorphic onto the image, and mapping the point P into the PIs. So we fix the region that we map to in the original sequence, such that, and now we want, of course, that the pullback of the metric g of t on the target manifold converges, or the gi's converges to the g of t. Right, so we pull back the gi's along phi's and from the mi's here, and this gives us the metric g of t in the limit. And by this we mean, of course, that this happens in all norms on each compact set uniformly. means uniform convergence in all norms on each compact subset. K of N. Okay, that's the concept, and now in practice you want to have slightly more freedom. So here I have assumed that this is on the same time interval. Now in reality you often have the solution of the sequence here being defined on time intervals AI up to BI, which is smaller, and then by rescaling you expand it, and then in the end you get a much larger time interval for the limit metric G of t. Again, and you could even shift the time by a parameter, so it doesn't have to be exactly the same time. You can translate the time, just like you can have a diffeomorphism. So I could have made this even more general and also fixed the times ti, just like I fixed the points pi, and move everything, say, to 0 in this limiting time interval. Crucial is, again, that you have this uniform convergence then on all compact sub-time intervals of your limiting time interval. And you want to have uniform convergence on all these compact sub-time intervals. Now, let's look at a picture to see why the concept has to be so general. Now, so the simplest case is the positive curvature case. Where you have the metric shrinking, really, and then of course you can choose pi equals p is fixed, and in this case it turns out you can just take phi to be the identity map from Sn to Sn with the different metrics to a fixed Sn, and this might be in the case where we rescaled the volume, this was even a fixed metric which was not changing in time at all. So in that case, we didn't have to do change the diffeomorphism as time was going on and as our sequence expanded. We could just rescale everywhere, choose the same points, and this was the simplest possible situation. Now, a more complicated setting would be, which I think already shows the main feature. So suppose we have this degenerate neck pinch where the singularity forms a cusp at some finite time t max, and then it turns out that if you take your sequence of points here just before, so look at this, just a moment before the cusp forms, then you will have sort of something to rescale here. If you now choose your sequence of points always at the tip, so two possibilities. A, choose pi to be p0, or p at the tip here, and then do this rescaling, then you will have, then I claim this converges to some complete manifold, which looks exactly like this. So take the limit. This part here gets completely blown away, so out of this compact thing, you get a non-compact thing, and you can choose your compact set to be sort of an exhaustion where you, at some distance here, where this is omega I, and you just let this grow, and then you get the rescaling of the flow. The rescaled matrix would be the GIs, and you get this evolution here, and you would get actually the diffeomorphisms would really be essentially flowing the these would be maps from larger and larger regions in this limiting manifold back to regions in these tips forming here. Now, if on the other hand, if you choose, so you get sort of, this gives you in the limit, paraboloid, and yeah, it's not an exact paraboloid, but it is a complete manifold which has this shape. But if you now choose your points, on the other hand, you choose your points pi to be somewhere here. So here we chose sort of. Right, so this is this picture rescaled just before taking the limit. Huh? So if you now choose points P1, P2, P3, which means you take points which are maybe very close to the tip, but not at the tip. And in this picture, they move out here to infinity. If you do this, choose pi off center the right way, then what you get to see is after you rescale around these guys, you see the picture far out here and you converge to a cylinder. A shrinking cylinder, Ricci flow. So it very much depends on how you choose these points pi in this procedure here, what kind of limiting manifold you get. That's why it's so important to include this into the concept of taking limits. And now the thing that I cannot prove, just have to quote, is that for such sequences, the thing you need in order to get compactness is curvature estimates. That's not surprising. That's why you have to rescale in order to get uniform curvature estimates. But you need the lower bound on the injectivity radius. So, so here's the compactness theorem. Now this goes back, of course, to Cheeger-Gromov in the case of just sequence of manifolds, and then Hamilton. When you have families, like in Ricci flow, and it says, so suppose MNI GI of T PI is a sequence of solutions to Ricci flow on some time interval AB. Well, it's really a sequence of time intervals with the fact that the sup over I of the sup of curvature, and the X is the MI and the T is in the AI BI of the Riemann tensor of the metric GI at T at X and T, if this is bounded, and crucially the infimum over I of the injectivity radius of Mn GI of T is uniformly bounded from 0. So this is the crucial assumption. If you have this bound on the injectivity radius, and you just need it in time 0, then there exists an Mn with a limiting metric G hat of T and a point, so that G hat of T is solution of Ricci flow, and it's complete, and you get that MNI GI of T P I converge to MN G of T and P. And this is, of course, just a subsequence. A subsequence converges. And of course, you need here a lower bound on the length of these time intervals. So BI minus AI has to be at least some positive epsilon. So you can take these limits and then you get this out. And now the proof idea here is, of course, that in view of Perelman's work, if you have the injectivity bounded at time 0, then you have it on the whole time interval by Perelman's work, and therefore you have you can apply the Cheeger-Gromov result also at the later times. That this is satisfied. This fact is follows from the non-collapsing that we proved. So sort of the compactness theorem was known to Hamilton, but the usability came from Federman, because only after Federman we know that the injectivity radius is bounded from below. Well, and once you have this, you can now apply this to rescale singularities. So with this, we can now rescaling singularities. So we're going to now assume that we have a solution of Ricci flow. U of t is a solution of Ricci flow on some maximal time interval, which is finite. And this is closed again, closed manifold. So we are exactly in the situation that we studied before. And then we know that the sup of the curvature on any sequence of times that approaches Ti that this number tends to infinity as Ti's approach the Tmax. You know, otherwise it would not, if this was bounded, we could extend the solution further, so we know this number goes to infinity, so let's give it a name. This is Mi. So Ti is now a sequence of times where we approach the singularity. We take the maximum curvature on the whole previous time interval. We know that tends to infinity, and now we want to rescale exactly at time Ti. We rescale exactly with this number, Mi. But we have to pick points. We have to say where do we rescale, right? So now we have to choose our points. And now I show it to you how it works in the case where we have a so-called essential blow-up sequence. In other words, where the curvature at the points that we pick is at least a fraction of the maximum curvature Mi. So now suppose Pi Ti is a sequence of events where the Riemann tensor at Pi Ti is at least some alpha times Mi. This is a so-called essential blow-up sequence. I make a comment on the non-essential blow-up sequences in a moment. And if we then set actually, maybe I should, yeah. There's no danger to confuse this with my sequence of manifolds. This is just a sequence of numbers. I'm going to leave the manifold for a moment to be the same and set Gi of t to be now I rescale with exactly this curvature. I want to blow up. I use the microscope, so I use the Riemann tensor at Pi Ti times the metric G, and I translate time into to make the new time ti's in the new thing to be the 0 time interval. So I take here t divided by exactly this. So I rescale the metric and I rescale time in the same way. Remember, metric scales like distance squared, which is the same as the scaling of time. So this is the correct scaling. And then you see such that when you compute ddt of di of t, you get this times the time derivative of g. So you get minus 2 the Ricci curvature of g at ti plus t over Riemann pi ti. And then you've got this factor, and then by the inner derivative, this cancels out exactly this, so you get that. But the Ricci curvature, as we know, with the indices down of a rescaled metric is exactly the same as the Ricci curvature. The Ricci curvature where both indices are down, this is just minus 2 Ricci of gi of t. Okay? So we get a solution of Ricci flow again, and but now we get that the new soup of over mn cos 0 ti of the Riemann of gi of t at x t is bounded by, if I rescale the metric by this, the curvature gets rescaled the other way around, so I get the curvature rescaled by exactly 1 over, so I get mi divided by Riemann at pi ti, but this is bigger than alpha mi, so this is less than alpha to the minus 1. And since alpha is uniform I have this uniform bound that I need for the compactness theorem on the curvature on my time intervals. And on the other hand, I also conclude that the Riemann tensor of the GI metric at times Ti at Pi Ti, of course this is equal to 1, because I'm exactly rescaling by this factor. So this means I'm getting something which is non-trivial. I make sure that I have some curvature somewhere at these points Pi. I make sure I get exactly the curvature 1 here. So this is making sure that I'm non-trivial. And now, on the other hand, I knew that by Perelman's work and our non-collapsing estimate, we know that the injectivity radius of the metric gi of t is bounded below by this number xi times the inverse of the maximum of the curvature. So here's an mi to the minus 1. But this means that the, this was for the metric g of t. This was the infimum over I on the set Mn cross 0 Ti up to here. Right? Up to here we had this, because the curvature is bounded. By that, we had shown that if we have that curvature bound, that we have this lower bound on the injectivity radius. Now, rescaling means that the infimum over I of the injectivity radius or on Mn of the matrix Gi of T, the rescales metric, that this is bigger than Xi, times, again, alpha times alpha. And this is now, of course, over the new time intervals, and the new time interval goes from this, the new time interval here, T, is between if the old interval was at capital Ti, then this is 0, so this new time interval goes up to 0, and it goes to minus Ti times R max, R at Riemann at Pi Ti. This is our rescale. Right? So the time interval gets longer by exactly this factor. So the solutions Gi, they live on this time interval here. And then we get that on this time interval, the injectivity radius is bounded below, because that scales exactly right. So we now have this uniform lower bound on the injectivity radius, and then compactness theorem applies, and we get sub-convergence to a limiting Ricci flow. So let's state that. Summary. So we get the theorem. I should attribute it. The first part, how to set up the thing, is due to Hamilton, and then, of course, the crucial lower bound of the injectivity radius is due to Perelman. If n and g of t is a solution of Ricci flow on a smooth closed manifold up to maximum time. Max, which is finite, then rescaling along an essential blow-up sequence yields a solution of Ricci flow on minus infinity 0 with well, actually, it lives a little bit longer, right? Because the capital T T max was bigger than our Ti, so we are rescaling around the Ti, so we get a solution, and our solution was bounded by, uniformly bounded up to T tilde, so we, up to 0, so we can extend it a little bit, so we get a solution which lives slightly longer than 0, but we get this uniform bound on minus infinity up to 0, get a uniform bound curvature, and we can make sure that at 0 the thing is non-trivial, is equal to 1. Now, the harder theorem, which I could not yet prove here, is that you can drop the essential. So in effect, so harder to prove, this is something that would have to be done in a continuation of these lectures. Much harder to prove is this is true along any blow-up sequence. But for that, you have to still prove certain things, and the thing that you need for this is an estimate on the gradient of the Riemann tensor independent of the and here I'm talking of n equals 3. This is so at n equals 3 along any blow-up sequence that you need that some estimate like this some estimates like this. So this is something I could not prove in this course. But what we can do in the three-dimensional case is that any rescaling for n equals 3 must have that all sectional curvatures. Remember, we proved these Hamilton-Ivy estimates saying that the negative part of the sectional curvature is small compared to the rest the sectional curvature. So now we know in 3 dimensions there's just the Ricci curvature, and we know the sectional curvature greater or equal to 0, so the scalar curvature is greater or equal to 0. So the Ricci tensor is then completely controlled by the scalar curvature, and it's non-trivial. We make sure that we get something non-trivial, so we must get sectional curvatures non-negative, and at least one of the sectional curvatures somewhere has to be strictly positive, because we rescale in such a way that we can rescale in such a way that you get something non-trivial. So in the three-dimensional case, because of the Hamilton-Ivy estimate, we know that the singularities are special. The rescaling procedure that we just carried out is always giving us a solution of Ricci flow which has non-negative sectional curvature. And that is a major restriction. Let's see how much we can already say now, and then let me give an outlook into the future. Okay, so the case n equals 3. So what we know so far. We know we can rescale when T tends to T max to get a solution of Ricci flow on some mn hat which is complete, and on a time interval which goes all the way to infinity. And we don't know what A is, we just know that A is bigger than 0, and it may or may not be infinite. And we know that the sectional curvature of G infinity, this metric, is greater or equal to 0. So much we know, and we know it's non-collapsed. And so M hat and G hat, G infinity is non-collapsed because that was a scaling invariant property, and which of course survives the rescaling procedure. And then there's a natural question, how many are there? Maybe we can classify them all. And indeed, that can be done. Let's see what we need for that and how much we can do already. Now, I did not show, I mentioned that there is a strong maximum principle for tensors. So we showed that if the Ricci tensor is greater or equal to 0, which is of course the case because of this, then it remains positive, and we also showed that if the sectional curvature is greater or equal to 0 in 3 dimensions, then it remains like this, everything in 3 dimensions. What I didn't prove, but I said, is that there is a strong maximum principle. In other words, if somewhere here in this interval the sectional curvature is equal to 0, then the manifold must be very special. So if we use a strong maximum principle for tensors, applied to the tensor Aij is equal to the Ricci tensor and to the tensor Bij equals Rij minus 1/2 Gij, actually plus, and this measures the sectional curvatures, then you can show either it has a zero everywhere or it is strictly positive. So strong maximum says you have two possibilities. Either the sectional curvatures are all positive everywhere, or B, the limiting manifold M hat n with G infinity of t splits as a two-dimensional manifold cross R, and the metric is a two-dimensional metric of t cross dr squared. In other words, you have either a two-dimensional solution of Ricci flow across a line, or you have something three-dimensional. Now, if you have a three-manifold with positive sectional curvature, it is well known and it's complete. There's two possibilities. If it's compact, so case A, 1, suppose it's compact. So if this split, if this thing, the singularity that we find, if M hat is compact, then we have a manifold of positive sectional curvature, which has certainly positive Ricci curvature, and we know exactly what Ricci flow is doing. That was Hamilton's original theorem. So in that case, we are done, because then it must be that M hat is equal to S3, or possibly a length space, and it must be the self-similar shrinking solution. In other words, this is the case where we're just back in the old theorem, in the old pinching theorem. It just took us a little while, for it may have started with something which was not positive Ricci curvature, but the rescaling is something of positive Ricci curvature, even positive sectional curvature, and then since it's existed for all time, it's easy to see it must be the shrinking sphere. So then we are done. The case A2 is, of course, that M hat is not compact. Now, if you have a non-compact but complete manifold with positive sectional curvature, it's well known it's diffeomorphic to R3. Now, what I cannot show you is how it looks like. So it took Perelman a lot of work, so this would be an extra chapter to show that there's a lot of work already in the original Perelman paper, that M3 has a cylindrical end because it has positive sectional curvature and it is non-collapsed and it is a solution which has existed for all time. Then you can show that it has a cylindrical end. In other words, it really looks like one of these pictures that I have been drawn, a bowl. And here at the end, this turns into a cylinder. So if you go far out, you see something which very much looks like a cylinder. Much later, it was shown that this thing is actually unique. This is unique, and this was shown by Simon Brandt. It is the so-called Bryant soliton, a axially symmetric, a rotationally symmetric solution of Ricci flow, which was found by Robert Bryant. But already Perelman knew that at the end it looks like a cylinder. And with precise estimate how far you have to go from here before you are arbitrarily close to a cylinder, Brandt showed it is rotationally symmetric everywhere. Okay, so it remains to say something about the case B. Now, in the case B, what can we say already at this stage? Now, in the B case, it just means we have to understand the two-dimensional case. So in the two-dimensional, so B is the case where we have a sigma 2 with a metric G infinity on an interval from minus infinity to some A. But we know the sectional curvature must be now strictly positive somewhere. The sectional curvature in this case is just the Gauss curvature. We know there's a maximum principle for the Gauss curvature, and since it's non-trivial, cannot be a plane, so it has to be positive Gauss curvature. So we know that G is positive. It has to be a metric with positive Gauss curvature. Now, again, we have B1. If it is compact, then we have the metric with positive Gauss curvature. This is the case we studied over 2 lectures. This is the case of the shrinking sphere, or the shrinking RP2. So in the case of a compact sigma 2, we know exactly what this must be. This must be the shrinking 2 sphere. Sigma 2 G of t infinity is the shrinking round 2 sphere. Which means that the original 3 manifold looked like a cylinder of a shrinking S2 which shrinks in finite time to a point. So this is exactly the situation that we expect when the original manifold was having a neck, and then inside this neck you form a singularity which looks like a shrinking cylinder. So this is exactly the situation that we detect in this way. Now, the case B2, now it could be, of course, also an RP2. The case B2 is a non-compact sigma 2. But we know again it has positive Gauss curvature. And remember, we proved in the case of positive Gauss curvature, remember we proved the Harnack inequality for the curvature. Now it turns out using that Harnack inequality for the Gauss curvature, you can show in this non-compact case that the thing also has to have a cylindrical end, that it has to be rotationally symmetric, it has to be a soliton solution. You can prove the only possibility such a thing with positive Gauss curvature, it must be the CDAR. Remember this cigar solution. But the cigar solution is collapsed. So this is ruled out. Because of non-collapse. So this possibility B2 does not occur. We only have this. So now we have shown essentially with our means along those blow-up sequences that we can understand, and I told you we at the moment understood only the essential blow-up sequences. Along those blow-up sequences we can only see the neck, or we can see the round sphere, or we can see this tip, which you expect if you have a degenerate neck pinch, if this bubble is so small that this surface gets stuck in here, and then at the tip, at the cusp, it looks like that. So we have identified with our rescaling analysis, at least in these cases of an essential blow-up sequence, that really we can only see the pictures that we expect. We see the neck, we see the round spheres, and we see the tips of the degenerate neck pinch where you form a cusp. This is all I could show to you in this course. But you can see now where this is going. Now we want to improve these results so that we see only these pictures along any blow-up sequence. So we have to make sure we can rescale everywhere, not just in the regions where the curvature is comparable to the maximum of the curvature. That is one task that we have to do. Once we have done that, we have proceeded very far, because now in all the cases that are not the round sphere, suppose we want to prove the Poincaré conjecture, in all those cases that are not the round sphere, we have then identified something where a cylinder occurs, either directly here in this picture, or at the end of this tip. So now, from there on, once we know that these are the only singularities, we can hope to cut off the neck. We can hope to somehow cut this and continue the flow after cutting. And cut off this horn and continue the flow. That of course involves showing this surgery construction. How do you cut? And when you restart the flow, you have to show that the flow is actually getting better. You have to show that after healing the patient like that, it takes a while until the next singularity happens, or you know precisely what is going on in some other way. In any case, you have to make sure that you only have to do these kinds of surgeries, these kinds of cuttings of necks or of these horns finitely often. And that means all the estimates that we proved have to survive the surgery procedure. And the hardest step in there is to show that the non-collapsing estimate survives the surgery procedure. Which would mean, for example, showing that the lower bound on the W functional is surviving the surgery procedure. Actually, I think nobody knows how to do that for the W functional. So we would have to study another second proof of Perelman, how to prove the non-collapsing, not using the W functional, but using something else called the L distance. And only when we have done that, then we can do the surgery procedure and put everything together to show that we can continue the flow as long as there is some volume there. And the final step then to prove the Poincaré conjecture would be to show that the volume itself has to be extinguished in some finite time, on all the manifolds that are possible counterexamples for the Poincaré conjecture. And with that, we would conclude that the whole manifold, if it is simply connected, can be decomposed into pieces which at the end only consists of spheres. And of course, the connected sum of spheres is a sphere again, so the original thing must have been a sphere. And that would conclude the Poincaré conjecture. But I've shown you the start of this program. I've shown you some of the major pieces like the two-dimensional case and the estimates of Perelman on the non-collapsing. So I would say we are about 40% of the way towards proving the whole thing. But that must be the stop for this semester. So thank you very much for your interest and thank you for your attention.